Well, this unit is going to focus on chi-squared, and we refer to as a chi-squared analysis. We're still going to look at this through significant testing eyes, but we're going to look at it through two different, one being goodness of fit and one being test for independence. That'll make more sense if we see some examples. But let's look at some basic stuff about the chi-squared. First of all, if you look at the picture of the chi-squared curve, it is a skewed right curve. Okay, so we're talking about skewed right data here. As you notice, when you have a low degrees of freedom and n is really small, you end up having a curve that has a big bulk here and then a tail down at the end. This is going to cause some problems, and it's going to end up interfering with our critical value a little bit. But as our sample size increases, as you'll notice, we start to get a really nice normal shape to this. In fact, once you get up to a sample size of 100, and that'll make a little more sense as we go through an example, you'll end up getting away from the skewed idea and completely get to a normal idea. Okay, and then we all know what skewed means. So let's go look at test of fit. So in this situation, what we're going to look at is the observed values compared to what we thought they should be. And this is the formula we're going to end up using. So we're going to take our observed values, subtract our expected values, so we're going to find the difference between the two, square that number, and then we're going to divide that by what we expect to get. Notice our degrees of freedom here. It's not based on your sample size. It's based on the number of categories. We have two assumptions here. Just like we said before, it has to be random. Then we have this that has to go here. You have to have each number, the expected value has to be greater than 5. There are a few exceptions to this, but we're not going to look at those. So check out my hypotheses here. These are always going to be the same. Nothing's going to change. This part's easy. There is no difference. We got exactly what we expected. There is a difference, so we don't match what we expected. The tail's always right. So you're going to find a critical value, and you have a chart for that in your packet. You're going to use this formula to find our test statistic, which in this case is going to be referred to by the symbol chi-squared. Then you decide, am I going to reject or fail to reject? And then I'm going to summarize. So these parts are the same as before. This part is going to be the same for each one of these. How we come up with these two, still critical and still test statistic, slightly different way we're going to find them. Let's go check out our example. So in our first example, they're talking about a census report, and they're giving us percentages that they believe to be true. Well, a study was going out, and if you counted these up, you'd end up with 200 over here. So 200 families were interviewed, and this is what they found. Well, if you wanted to find your expected values, all you'd have to do is find 68% of 200, and that would be your expected value because you expect 68% of 200 have 2 parents in the household. Once you got those numbers, then you would take the observed number, which in the case of 2 parents is 120, the expected number that you get, subtract them. All that gets added down here is the square. Leave the last column for now, the last row for now. Fill in these next 3 rows, pause the video, and come back when you're ready. Hopefully you got these numbers. 68% of 200 gave me the 136. When I subtracted 120 and 136, I got negative 16. When I squared negative 16, I got positive 256. Keep in mind, all the numbers in this row have to be positive because you're squaring a number. Well, this last row is how we're going to find our test statistic. So you're going to take the numbers you just got, your observed minus your expected squared. You're going to divide those by the numbers that you see up here in this row for expected. So for example, you're going to do 256 divided by 136. Pause the video, go ahead and get those numbers in there, rounding to 2 decimal places. So hopefully you got those numbers. So now we have those numbers. What you're actually going to do is a summation of this list. You're going to add all those numbers together. And if you do that, you'll end up with 43.16. We'll come back to what that number means in 1 second. So let's talk about our alternate and null hypothesis here. In this particular case, and all of these tests for goodness of fit, if you think about what we talked about before, the null and the alternative hypothesis are going to stay the same. So what ends up happening is and you'd write this out, our null hypothesis would be that the percentages match what was expected. So we got our observed values, the 120, the 40, the 30, the 10, they fit essentially in with the 68%, the 23%, and so on and so forth. The alternate would be that there is a difference, that there is some difference. And then ultimately we try and figure out where is that difference, what is the reason for it. Now we're going to have to look at our chi-squared chart. So go ahead and take that out. We need to figure out how many degrees of freedom there is here. Well, there's 4 categories: 2 parents, mother only, father only, no parents. So my degrees of freedom is going to be 4 minus 1, or 3. If you look at your chart, we're doing this at a 5% significance. So what you want to do is you want to go to that chart, look up the 0.05 column, and you're going to find a critical value of 7.82. So what does this mean? Well, think about what it meant before when we had our critical value and we had our test statistic. If you think about the chi-square curve that looks like this, skewed to the right, the critical value is going to be my border. Anything beyond that is going to be a fail. 43 is way up here. So in this case, we're going to fail to reject, or reject. In this case, we're going to reject the null hypothesis. Well, think about what that meant. The null hypothesis was that the percentages matched. So pause the video, take a second, and ask yourself, what does this mean? Well, the percentages don't seem to match. So this sample, talking about this particular school district, which was a large, diverse school district, the percentages do not seem to match what was reported in the census. Then the next question we'd ask ourselves is, where did the biggest area of concern come in? Where was the biggest culprit in kicking up my test statistic? In this case, the father only is so astronomically high from where we expected it to be. That was a big reason the chi-square was so high.